For most of human history, time was treated as something absolute, a universal river flowing forward at the same speed for everyone, everywhere. The past was fixed, the future was unknown, and the present was the only place reality could exist. This idea shaped religion, philosophy, and eventually science itself. Time travel, under this worldview, was pure fantasy, a myth reserved for gods, prophets, and storytellers. Then, in the early 20th century, something extraordinary happened. Science broke time, not metaphorically, mathematically. Albert Einstein introduced a concept that quietly destroyed the idea of a universal clock. According to his theory of relativity, time does not flow independently of space. It is woven together with it, forming a single structure known as space-time. This was not a philosophical claim. It was a physical one. Time could stretch. It could slow down. It could move at different rates, depending on motion and gravity. Suddenly, time was no longer a fixed background of reality. It became something dynamic. And once time became flexible, time travel stopped being impossible and became conditional. This was the first, true breakthrough. Einstein showed that time travel is not a question of imagination. It is a question of physics. If space-time can bend, then paths through time can bend as well. At first, this realization felt harmless. After all, even if time could slow down, it didn't mean we could move freely through it. But as physicists explored Einstein's equations more deeply, unsettling consequences began to emerge. Some solutions suggested that space-time could curve so dramatically that time itself could loop back on itself. Others implied that extreme motion could propel an observer far into the future, while the rest of the universe aged normally. None of this required science fiction machines, no glowing portals, no paradoxical buttons, just the laws of nature, taken seriously. This marked a crucial separation between science fiction and science. Science fiction treats time travel as a tool, something characters use. Physics treats time travel as a consequence, something that happens when reality is pushed to extremes. That difference matters. Because real physics does not care about storytelling convenience. It cares about consistency, and consistency is where time travel becomes deeply uncomfortable. The moment time stopped being absolute, causality became fragile. Cause and effect, once thought to flow in a simple line, now depended on perspective. Events that were simultaneous for one observer might occur at different times for another. This alone shattered the idea of a single, objective now. There is no universal present. Only relative presence. That fact has been experimentally confirmed. Time dilation has been measured using atomic clocks. Clocks flown on airplanes tick differently than clocks on the ground. Astronauts age slightly slower than people on Earth. These are not theories anymore. They are measurements, and they force us to accept something profoundly strange. We are already traveling through time, just not in dramatic ways. Every human alive experiences time at a slightly different rate depending on motion and gravity. The differences are tiny, but they are real. Time travel into the future is not speculative. It is happening right now. The only reason it doesn't feel revolutionary is scale. The universe allows time travel, but it demands extreme conditions. Near light speeds, intense gravitational fields, enormous inertial conditions, far beyond everyday life. But the door is not closed. And once physics opened that door, theorists began asking dangerous questions. If time can slow down, can it stop? If space-time can it bend back on itself? And if the laws of physics allow such paths, does the universe actually permit them to exist? These questions marked the true beginning of scientific time travel research. Not fantasies about visiting dinosaurs or future cities, but rigorous attempts to understand what the structure of reality allows. And this is where science fiction often gets it wrong. Movies suggest time travel is about changing history. Physics suggests time travel is about constraints. The universe appears less concerned with what we want to do, and far more concerned with protecting consistency. This leads to a disturbing implication. If time travel is possible, it may not grant freedom. It may enforce rules. Rules that prevent paradoxes. Rules that limit intervention. Rules that make time travel far more restrictive than fiction ever imagined. In other words, The universe may allow time travel, but only on its own terms. This realization reshaped the entire field. Time travel stopped being a question of how do we build it, and became a question of what does reality tolerate. That shift is the foundation of every serious breakthrough that followed, and it leads directly to the next step. Because if time itself is flexible, measurable, and relative, then traveling into the future is not speculation. It is already proven, and that brings us to the next breakthrough, where theory becomes experiment, and fiction collapses under data. Time dilation. How physics already allows travel to the future. If time travel sounds like science fiction, then this fact should feel unsettling. According to modern physics, traveling into the future is not hypothetical. It is already happening, not dramatically, not visibly, but measurably. The breakthrough that makes this possible is called time dilation, and it emerges directly from Einstein's theory of relativity. It reveals something deeply counterintuitive. Time does not pass at the same rate for everyone. The faster you move through space, the slower you move through time. This is not a metaphor. It is a physical law. When an object approaches the speed of light, time for that object begins to slow relative to everything else. From the traveler's perspective, nothing feels strange. Their clock ticks normally. Their body ages normally. But to the outside world, their time is dragging behind. This means that motion itself becomes a kind of time machine. If a spacecraft could travel close enough to the speed of light, a journey lasting a few years for the crew could correspond to decades or even centuries passing on Earth. When the travelers return, they've effectively leapt into the future. This effect has been experimentally confirmed. Atomic clocks flown on commercial aircraft tick more slowly than identical clocks left on the ground. The difference is tiny, measured in nanoseconds. But at Israel, astronauts aboard the International Space Station age slightly less than people on Earth because they are moving faster and experiencing weaker gravity. These are not theoretical predictions. They are measurements. Time dilation is no longer debated. It is built into modern technology. In fact, without accounting for time dilation, GPS systems would fail. The satellites orbiting Earth experience time differently than receivers on the ground. Engineers must correct for relativistic effects, or navigation errors would accumulate rapidly. Every time you use GPS, you are relying on time travel math. This alone destroys the idea that time travel belongs only to fiction. The real limitation is not whether time travel is possible. It is how much time you can move through. To achieve significant future travel, you must approach extreme velocities, and this is where reality becomes unforgiving. As an object accelerates closer to the speed of light, its energy requirements increase dramatically, not linearly, exponentially. Reaching 90% of light speed already demands unimaginable energy. Reaching 99.9% pushes beyond anything humanity can currently generate. Nature allows the effect. Technology cannot yet exploit it. This is a recurring theme in time travel theory. Physics opens the door. Reality narrows the doorway. But even this limitation reveals something profound. Time travel into the future does not violate causality. It does not create paradoxes. It does not threaten the structure of reality. It simply stretches the timeline. From a physics standpoint, traveling into the future is the safest form of time travel imaginable. No events are altered. No causes precede effects. History remains intact. You leave. Time passes. You arrive later. Science fiction often ignores this because it lacks drama. But scientifically, this is the most realistic version of time travel humanity could ever achieve. It raises a strange philosophical consequence. If time travel into the future is possible, then different observers can legitimately experience vastly different versions of history. One person could live through an era while another skips over it entirely. For one observer, decades pass. For another, only moments. History becomes observer-dependent, and this is not speculation. It is a direct consequence of relativity. The universe does not enforce a single shared timeline. It allows multiple personal timelines, all consistent, all real. This challenges how we think about aging, progress, and even survival. In extreme theoretical scenarios, a civilization capable of relativistic travel could send explorers into the far future of the universe. They would witness the slow death of stars, the expansion of space, an epics no human on Earth could ever experience. Not by magic, be motion. This realization fundamentally separates science from fiction. Movies depict time travel as control. Physics reveals it as surrender. You don't command time. You submit to its rules. Time dilation gives us a glimpse of what time travel actually looks like when stripped of fantasy. It is subtle, unforgiving, and entirely governed by energy and geometry. And it leads to an even more unsettling question. If motion can bend time forward, what happens when space-time itself bends? Because speed is not the only way to distort time. Gravity does it too. And when gravity becomes extreme enough, time behaves in ways that challenge not just fiction, but our deepest assumptions about reality. That is where the next breakthrough begins. Few ideas blur the line between science and science fiction as perfectly as wormholes. In their simplest form, wormholes are theoretical bridges. Enter one end, exit another, without crossing the space in between. From the outside, the journey could take years. From the inside, it could take moments. But here is where the theory becomes truly disturbing. If time flows differently at each end of a wormhole, then moving through it does not just relocate you in space, it displaces you in time. This is not speculation layered on fiction. It is a direct consequence of relativity. Time does not flow uniformly across space-time. Gravity and motion distort it. If one mouth of a wormhole experiences strong gravitational effects or relativistic motion while the other does not, the clocks at each end will no longer agree. That difference in clock rates turns a spatial shortcut into a temporal one. In theory, a traveler could enter a wormhole and emerge in a different era. But theory is where comfort ends, because wormholes come with severe problems. The first is stability. They are physically hostile. Nature does not forbid them outright, but it offers no easy path to make them real. And even if a wormhole could be stabilized, a deeper problem emerges. Causality. A time travel-capable wormhole opens the door to effects could precede causes. Events could interfere with their own origins. Information could appear without a clear source. Physics does not tolerate this easily. Some theorists argue that wormholes capable of time travel would trigger feedback mechanisms that destroy them before paradoxes can occur. Others propose that quantum effects would destabilize the wormhole the moment it becomes a time machine. This idea evolved into a broader principle known as chronology protection. The universe, it seems, may allow mathematical loopholes, but actively prevents them from becoming physically exploitable. Wormholes are a perfect example. They sit right at the edge of what physics permits, teasing possibility without offering practice. Science fiction often portrays wormholes as tools. Stable, navigable, reliable. Real physics treats them as fragile, dangerous, and likely. Yet, wormholes remain one of the most important breakthroughs in time travel theory. Not because we can use them, but because they reveal something profound. Space-time is not rigid. It can twist. It can fold. It can connect distant points in ways that defy intuition. That alone changes how we understand reality. Even if wormholes are never engineered, their existence as solutions tells us that the universe's geometry is far more flexible than once believed. And flexibility is the foundation of time travel. Another unsettling implication follows. If wormholes exist even briefly in the early universe, they could leave signatures. Gravitational anomalies, unusual lensing effects, patterns in cosmic background radiation. Scientists are not just dreaming about wormholes. They are searching for their fingerprints. Not to build time machines, but to understand the limits of space-time itself. Wormholes force us to confront a difficult truth. Time travel is not impossible because it violates physics. It is dangerous because it exposes how fragile causality might be. And when causality becomes fragile, reality itself becomes unstable. This brings us to the next breakthrough, one even more disturbing than wormholes. Because what if space-time doesn't just connect distant points? What if it loops back on itself, not through tunnels, but through curves? Curves that allow the past to coexist with the present. That is where time travel stops being about shortcuts and becomes about paradox. Closed, timelike curves. When time loops back on itself until now, time travel has sounded difficult, but orderly. Move fast enough, and you drift into the future. Bend space-time with extreme gravity, and shortcuts might appear. Use wormholes and distance. Even time could theoretically collapse, but closed, time-like curves change the tone completely. They do not suggest traveling through time. They suggest being trapped inside it. A closed time-like curve is a solution to Einstein's equations where space-time bends so extremely that an object can follow a path that eventually returns it to its own past. Not through a machine, not through a tunnel, through geometry. In these models, time does not flow forward in a straight line. It curves back on itself, forming a loop. An object following that loop would experience time normally from its own perspective, yet still arrive at an earlier moment in the universe's history. This is not speculative storytelling. These solutions exist within accepted mathematical frameworks of general relativity. The most famous examples appear near extreme gravitational environments, such as rotating black holes, known as Kerr black holes. In theory, the spacetime around these objects becomes so twisted that closed time-like curves can form. If such curves exist, time travel to the past becomes mathematically possible. And this is where physics begins to feel deeply uncomfortable, because traveling to the past threatens causality itself. Cause and effect are the backbone of physics. Events happen for reasons. Effects follow causes. Remove that structure, and predictability collapses. Closed time-like curves allow scenarios where effects can become their own causes. Information could exist without an origin. Actions could erase the reasons they occurred. Events could be self-consistent, yet logically disturbing. This gives rise to the classic time travel paradoxes, often portrayed in fiction, but here they emerge directly from equations. Physicists responded to this problem not by rejecting the math, but by trying to contain its consequences. One proposed solution is the self-consistency principle. According to this idea, events occurring along closed time-like curves are constrained in such a way that paradoxes cannot arise. History cannot be changed, only fulfilled. If you travel to the past, your actions were always part of that past. No contradictions? No alternate outcomes? The universe becomes rigidly consistent. This sounds naot until you consider what it implies. Free will becomes questionable. Choice becomes illusion. Every action is locked into a loop that cannot be broken. Time travel, under this model, does not grant power. It removes Italiano. Another response to closed time-like curves comes from quantum physics. Some researchers argue that quantum effects would destabilize any region of spacetime where such curves form. The moment a loop threatens causality, quantum fluctuations grow uncontrollably, destroying the structure before it can be used. This idea aligns with a broader concept known as chronology protection. The hypothesis that the laws of physics actively prevent time machines from forming, not by forbidding them mathematically, but by making them physically impossible to sustain. In this view, closed, timelike curves are like fault lines in space. The equations allow them, but the universe refuses to let them stabilize. Yet, no definitive proof exists, and that uncertainty is what keeps these ideas alive. Closed timelike curves are not engineering blueprints. They are stress tests for reality. They show us where our theories begin to contradict our intuitions, where math allows things that logic resists, and they raise a haunting possibility. What if the universe does not prohibit time travel, but merely restricts how it can be experienced? What if time travel exists only in ways that preserve consistency, trapping travelers in loops rather than allowing change? This would mean time travel is not a tool for rewriting history. It is a prison, a structure where events repeat, not because they must, but because they already did. Science fiction often imagines time travelers as agents of chaos or heroes of change. Closed time-like curves suggest something far darker, a universe that allows loops, but denies freedom. This concept forces physicists to confront an uncomfortable truth. Time travel may be compatible with physics, but incompatible with human expectations. And that realization leads directly to the next breakthrough, because there may be another way to escape paradox. Not by enforcing consistency, but by abandoning the idea of a single timeline altogether. Quantum mechanics and multiple timelines, escaping paradox by fracturing reality. And if causality collapses, physics itself loses meaning. For decades, this dilemma appeared unsolvable. Then quantum mechanics entered the discussion and quietly rewrote the rules. At its deepest level, it describes probabilities, superpositions, and branching outcomes. Because there is no single past to change. According to this view, every quantum event causes reality to branch. Under this framework, traveling to the past would not rewrite your original history. Instead, it would place you into a different branch, a parallel timeline that diverges from the moment you arrive. You cannot kill your own grandfather, because the moment you try, you are no longer in the timeline where you were born. Your original history remains untouched. From a mathematical standpoint, this is elegant. It preserves causality. It avoids contradiction. But the cost is staggering. And it has serious proponents. If multiple timelines exist, how would we detect them? A time traveler could enter another branch, but never return to the original one. From the traveler's perspective, time travel becomes irreversible. It becomes an act of abandonment, leaving your original reality behind forever. Another unsettling implication follows. If multiple timelines exist, then every possible version of history already exists somewhere, not just alternate futures, alternate pasts. This reframes the concept of destiny. Nothing is prevented. Nothing is erased. Everything happens, just not in the same universe. This interpretation also raises deep philosophical questions. If countless versions of you exist, which one is you? Is identity tied to continuity, or merely perception? Quantum time travel doesn't just challenge physics. It challenges the concept of self. Critics of this idea argue that the many-worlds interpretation, while mathematically consistent, lacks experimental proof. We have no way to observe other branches directly. Allowing all possibilities while preventing interference between them. But this solution is not comforting. It replaces the fear of paradox with the fear of your actions matter, but only locally. Somewhere else, every alternative unfolds. And if time travel were ever achieved under quantum rules, it would not grant control over history. It would fracture it further. Which leads to a final, unavoidable question. If the universe allows time travel only under extreme conditions, only in ways that prevent control, only in forms that fracture reality or trap events in loops, is time travel something the universe wants to permit at all, or is it something it tolerates reluctantly? That question leads directly to the final breakthrough, because some physicists believe the universe has a built-in defense system, a way to predict time itself. When physicists attempted to model realistic time machines using wormholes or closed timelike curves, they repeatedly encountered the same problem. As soon as a system approached the point where time travel to the past became possible, quantum effects exploded. Energy densities spiked, vacuum fluctuations intensified. Instabilities grew without bound. It was as if reality itself rejected the configuration. This suggests something profound. Causality may not be a fragile byproduct of physics. It may be a fundamental feature, aggressively enforced. But destroys the implementation. Quantum timelines avoid paradox by isolating realities. Physics suggests the opposite. If time travel truly threatened the structure of reality, a self-correcting mechanism would be the most efficient solution. It is an immune response. Any attempt to alter causality could be erased before it completes, not retroactively, but preventively. And yet, even this does not fully close the case. Chronology protection remains a conjecture. It is elegant. It is persuasive. Physics offers constraint, and perhaps that is the true breakthrough. Not learning how to travel through time, but understanding why the universe makes it so difficult. Time may not be a river we can navigate at will. It may be a structure we can only glimpse under extraordinary circumstances, before it snaps back into place. If time travel ever becomes real, it will not look like movies. It is philosophical. And where the universe quietly enforces its own rules, subscribe to because the deepest mysteries aren't hiding in the past or the future. They're embedded in the structure of reality itself.